The first talk this afternoon is Luca MIGLIORINI, and we'll talk about HOMFLY polynomials and the Hilbert schemes of plane curves.
So, thanks a lot. It's an honor. And so, what I'm going to talk about is an amazing formula conjectured by Alexei Oblomkov and Vivek Shende. So this was conjecture, I think, in 2010. And then there were two refinements. So this was by Emmanuel Diaconescu, Zheng Hua, and Ian Soibelman. I think more or less at the beginning of 2012. And then it was proved by Davesh Maulik at the end of 2012. So it's, as a conjecture, it had a short life, and but actually there are many possible developments. And the conjecture is, well, a conjecture in a sense in topology of algebraic varieties at the zero level, that is topology of curves. So let me first introduce a bit of notation and just remind you of some elementary things. So we start with a two variables polynomial with complex coefficients. So let's denote the origin by P and assume that F vanishing at the origin. So by C, we just consider the zero set of F, and we assume that C is reduced. So that is that F has no multiple factors. And of course, P is said to be a singular point if the partial derivatives vanish at the point P. So as an example, which I will consider just at several steps, we can take f x y to be y to the r minus x to the s, with r s bigger than or equal to 2. So special cases, if for r and s 2, we have what is called a node. So English is very convenient for this talk because there is a word for node and a word for not, which are two different things, and they will both come in the picture. So this is a node. In Italian, it's always nodo, and that's, I mean, it doesn't help. And for 2, 3, then we have what is called a cusp. And there are a few basic definitions about singular points. So one definition is definition of branches at P. So this goes as follows. So F may factor, so let's say that this is a factorization into irreducible, but not in the polynomial rings, but in some more local rings, so something like formal power series, or what is the same, convergent power series. And in this case, we have the curves CIs, which are given as the zero set. I mean, in the convergent business, we have the zero set of these factors. And so these are called the analytic branches. And this may differ from irreducible components because you can have analytic branches corresponding to the same irreducible component. But actually, just to simplify the exposition, I will assume that such phenomenon doesn't hold. So I will assume from now on that, let's say that, I mean that this factorization in the convergent power series already holds at the level of polynomials. Just so I assume basically that every irreducible component of C, let's say, contributes to one branch, a single branch. And well, branches are, as you may know, that in one-to-one correspondence with points in the inverse image of the point in the normalization. So we have these branches, and so let's see, Monte. No. Ah, let's see. Yes. Okay, and between branches you have intersection numbers. So if you have two branches, Ci, Cj, you define their intersection number as the dimension, let's say, of the quotient, say, formal power series, modulo the ideal generated by the local equation of these two branches. And this is, I mean, by definition, a positive integer. And another notion that I will shortly need is what? Is the well, the definition is that the Milnor number so the Milnor number is by definition the dimension of this quotient, so the quotient of, let's say, formal power series by the so-called Jacobian ideal, that is the ideal generated by partial derivatives. So this is not obvious that this is a finite dimensional vector space, but actually, under the hypothesis that C is reduced, this is actually true. So this is a primary ideal. So this Milnor number will come in the original conjecture of Oblomkov and Shende, and it has a nice topological meaning on which I don't want to insist now. And the last fact that I want to recall is the so-called Newton-Puiseux theorem. And this says that every branch admits a local parametrization of the form, well, after a coordinate change, of the form x equals to t to the a for some a, y, just a power series. Or, as it often one writes y as a function of x as a Puiseux power series. So x to the n over a. And actually, a more convenient way to write this is to write something like x to the q0 over pi 0 plus a0 plus x over q1 over pi 0 p1 and so on. Okay, we will see in a minute why this is this way of writing the Puiseux development is convenient. Okay, so for the moment, this is, well, maybe I should make at least, in that example, of course, in the example up there, so if, so let's say that in the example, y to the r minus x to the s, so there are d branches where d is the greatest common denominator of r and s. And so in particular, if r and s are coprime, then there is only one branch. And in this case, the Puiseux development is just x equals t to the r, y equal t to the s. In the case in which there is divisibility, then you have d different branches, and each one is a curve of type y to the r over d minus x to the s over d. Okay, there are d different branches. Okay, now I want to translate a few of these facts on the link side, but first I have to tell you what the link is, and now again I will so the link is a classical construction and goes as follows. So you have say that here you have the complex plane, here you have your curve, here you have the singular point. Now take, so the idea of the link goes back to, I don't know, I mean, maybe Keller, and of course the book of Milnor on singularity of a complex hypersurface is a masterpiece of this. But anyhow, you take a small three-dimensional sphere, so this is a S3 of a small radius. Then the intersection here is what? The intersection of S3 for, say, radius epsilon with a curve is, well, first of all, for epsilon small enough, is just independent of what the radius is. And so this is oriented because both are oriented, and this is an intersection. One-dimensional, compact, manifold. So in particular, this is this joint union of oriented S1s. So this is a bunch of circles inside a three-dimensional spheres. And so this is precisely what is called a link. Okay? So the link of a singularity is a link. So this is the link of C at P. So I will usually call it with this fancy-looking L. Examples. If P is a non-singular point, then it's easily seen that the link is the unknot. It's an S1 trivially embedded in, I mean, standardly embedded in S3. In the case y squared minus x squared, which has two components, then these are, if you intersect with the sphere, you see two fibers of the Hopf vibration. So therefore, the link is something like this, and the orientation, I think, is this one. So this is what is called the Hopf link. And so this is first example, second example. Third example, y squared minus x cubed, then what you immediately see with the parametrization, which is hidden behind the blackboard, but I may remind you that the link is actually e to the 2 times I t y equals e to the 3 I t. So this is a knot contained, standardly contained in a 2-dimensional torus. So this is a so-called the positive trefoil knot, and a way of drawing it is something like this. Oh, yes. And in general, if you take y to the r minus x to the s with r and s coprime, what you find is the link is still a toral knot of type rs, which you realize by taking a braid with r strands, taking the, so these are r strands. Then you take this braid, which is actually the product of the positive generators of the braid group. You iterate this braid s times, and then you close it. Okay, that's what you get. And I'm spending a bit of time on this because this is an example, but it's actually the example. So what I want to do now is to have the right blackboard. Yes, this one. So how these facts translate especially, I mean, not the Milnor number doesn't, but this one and this one translate on the link side. So on the link side, branches correspond to connected components of the link. The intersection numbers so Ci times Cj translates into the linking number of the corresponding connected components. So the link, if you have 2 knots in a S3, you can define the linking number, which tells you how many times one component winds around the other. Okay, you can define it in many ways. I think the oldest definition is the one by Gauss with the double integral, which everybody learns in studying electromagnetism, hopefully. I mean, it takes some time to understand that definition, but I mean, that's one. So anyhow, intersection numbers of components correspond to linking numbers. So this says in particular that already that algebraic links, that is, links which are obtained by this construction, are quite special, because all the components have positive linking numbers. So for instance, the Borromean rings are not algebraic links, because the Borromean links, if you take a pair, they're not linked. So there are actually, so links which are obtained by this construction have very special properties. So this is one special property. And another special property comes precisely by the Newton-Puiseux theorem. So the Newton-Puiseux theorem implies that every component of the link is an iterated toral knot. So I think it's worth spending just a short comment after I choose on which blackboard to put it, which is the, no. Sorry, I can't. No, that's okay. Makes sense. So, what do I mean by iterated toral knot? By iterated toral knot, I mean the following. Let me give an example. So, for instance, x t to the 4th, y t to the 6th plus, say, rho t to the 7th. So this is a parametrization like a Newton-Poisson parametrization of the singularity. So you see that if you don't consider this, so the link will be parameterized something like exp 4i t, y exp 6i t plus rho exp e 7t. So if you just decide not to look at this point, you see a 2-3, I mean, a 2-3 knot. I mean, the one that's hidden in the, let's see, no, can't make it. No. Okay, let's forget about this. So you see a 2-3 knot, like the one I had drawn before. And then you can consider this term as a small perturbation of this. So you see that when t goes from 0 to 2 pi, you see that for every x, there are 4 values of y. Every value of x is taken 4 times, so there are 4 values of y. And actually, you can think of being some sort of the 2 points which do this 2-3 knot, and then actually the 4 points are just orbiting around. So this is a sort of a superposition of a toral knot over another toral knot. And the Newton-Poisson theorem says that every component is done by iterating this construction. So there are toral knots wrapped around toral knots, wrapped around toral knots, and so on. So these links are very special. Now, okay, so this was just introduction. Oh, maybe I should point out the following. So, analytic singularities of curves have moduli, whereas links, in a sense, don't. So the example of what I want to give, so for instance, of what I mean, if you take 4 lines meeting at point, then you can change coordinates so to fix 3 lines. But then the other, I mean, you have the cross ratio as an invariant. So for different values of the cross ratio, you have analytically non-isomorphic singularities, whereas the link stays the same. Okay, so I mean, it stays 4 circles linked to each other with linking number 1. Okay, so the conjecture of Oblomkov and Shende deals with the following problem. So links, there is an important invariant for links, which is the many letters polynomials. So this is a polynomial in 2 variables. Actually, these 2 variables can be also invert. So this is like something like V plus or minus 1, S plus or minus 1. So this is determined by the following properties. So the first property is just a normalization property, which says that the polynomial of the unknot is this one here. And the second property is the so-called skein relation, which tells how the polynomials of, well, if you have a crossing, so you represent a link by some diagram in the plane, some oriented diagram in the plane. So at some points you have crossings, and there is an indication of what goes over and what goes under. So out of a diagram, you can construct two new diagrams just by swapping the crossing or just by eliminating it. So the scale relation is that V minus 1 of the polynomial of the diagram with this guy minus V of the polynomial with this guy equals the polynomial of this guy times S minus 1. And it is a theorem that this polynomial is well defined. That is, doesn't depend on how you project your knot on the plane to obtain a diagram, on which sequence of skein relations you apply to get to the polynomial. So the problem raised by the conjecture of Oblomkov and Shende is whether if L is an algebraic link, that is, by this I mean a link arising from the construction as an intersection of a plane curve with a sphere, is there an expression, is there an algebraic expression in terms of C and P for this polynomial? Okay. So in a sense of, like the linking number of two components is from the algebraic point of view is just the intersection number of connected components. So the question is, can I concoct something from the datum of the plane curve and its singularity, which gives this topological invariant? And so the conjecture is was the following. So the conjecture is that this polynomial can be expressed as follows. So this is the conjecture of Oblomkov and Shende. And I'll spend a few minutes telling what these terms are. So I guess the first thing to be explained is this guy here. Okay, so CPL, which is sometimes called the punctual Hilbert scheme of the curve. So this is an algebraic variety, which I will consider with its reduced structure. So I don't want to discuss its scheme structure. So this is an algebraic variety parameterizing subschemes Z of my curve such that the reduced subscheme is just a point. So we have this singular point. So we are looking at subschemes which are concentrated only at the singular points, and such that the dimension of the space of regular functions on these subschemes is L. Or maybe equivalently, maybe this is more understandable, I don't know. Equivalently, these are the same as ideals. So ideals in the local ring of the curve at P, such that the radical is the maximal ideal of this local ring, and the dimension of the quotient over C is N. Okay. So L, yes, L. Okay. So if P were a non-singular point, this would be kind of a dull thing. Okay, ideal, we basically would look only to ideals in the formal power series in one variable. This is a principal ideal domain, so in co-length L, there's only the ideal T to the L. So in this case, you'd have just points, which, by the way, okay, in this case, this M to the I would be 1, because you'll see that M to the I is the number of generators. So this guy will be I, and this sum would just become 1 minus V square sum S to the 2L. So V over S. So the Milnor number is of a smooth point is 1. So this guy wouldn't be here. No, it would be no, it's 0. So would be S over V, and this guy will be 1 minus S square. So up to some some mistake in computation, you will find V minus 1 over S minus 1, which is precisely the polynomial of the unknot. So at least in the case of a smooth point, this works. But in general, when the point is not smooth, then you can have such a sort of a rich scheme structure over a singular point. So for example, let's see. So for example, if P is a node, so something like this, here, then the Hilbert scheme of length L consists of a tree of L minus 1 P1s. Okay, with some special points which correspond, so these special points correspond to monomial ideals. So in general, this Hilbert scheme is kind of is very hard to compute and to understand. So so I told you what is the this pointwise Hilbert scheme. So I have to tell you about this M of I. So M is a function from Cp to the L to, well, natural integers. So M of an ideal I is the minimal number of generators of I, which by Nakayama lemma is the same as the dimension as a vector space of I modulo MP I. So this is a constructible function. So for instance, this function is what? Is actually 2 at these special points and 1 otherwise in these examples, because these ideals are principal. So these are constructible functions. So what is that strange-looking integral? So the strange-looking integral means the following. So write this Hilbert scheme as a disjoint union. So this thing here is n minus 1 of the number k. So it's the locus where you need k generators for the ideal. So the that integral is integral against the Euler characteristic. So this thing here means just sum over k 1 minus v squared to the k times the topological Euler characteristic of the corresponding level set. So this is a notion of integral against the Euler characteristic, which was introduced, I think, by Oleg Viro. Okay? So I think more or less I've explained all. Let me see if I manage to get them now. Right? I mean, you should give a course to the BOURBAKI speakers, because I mean to me. Okay. So I think I've explained all the terms in this formula, which I think is quite remarkable. So this has to do only with the analytic structure of the singularity. So this thing a priori depends on the moduli of the singularities, which, as I said, can actually happen. So there are a few consequences of this formula. So the first is that the right-hand side is independent of moduli. What happened?
Don't worry about it. There's a former screen which doesn't work anymore.
Okay. So this is independent of moduli of the singular point. And the second remarkable thing is that, I mean, the right-hand side, which a priori a formal power series, it's actually a rational power series with denominators which are given by, at worst, powers of s minus 1. Okay? So this is a strong statement about the growth of these terms. And also, you see, the HOMFLY polynomial has an obvious symmetry. Let's see. So P, L, V, S has a symmetry sending S to minus S minus 1, if you look at the definition, which is not at all evident from this expression. Okay? And actually, this is this was actually already noticed by Pandaripanda and Thomas. It's actually a hidden form of Serre duality in this case. Okay. So this is a kind of a remarkable formula. And so I'll try to use the very little time that I still have to tell you about the refinement of Diaconescu, Wu, and Seubelman, because it actually contains some important insight. So the insight of Diaconescu, Wu, and Seubelman is first, is that this is actually, so Oblomkov Shende conjecture is better understood by adding an extra dimension. So also according to what Davesh Maulik told me, I mean, a real breakthrough was to understand that this is not a problem in plane geometry of curves, but actually it's a hidden problem in threefolds. So this goes as follows. Actually, an extra dimension, so actually more precisely going to local Calabi-Yau threefolds. So let me denote by Y the total space of the vector bundle O minus 1 plus O minus 1 over P1. Okay? So you have P1 here, and then you have, for every point in P1, you have some, so this will be C2. If you want to write an atlas, you take two open sets, like C3, and then you have a coordinate Z, C1, C2, W, zeta1, zeta2, and coordinate changes are W, Z to the minus 1, Z1 equals something like Z, C1, Z2 equals Z, C2. So to see that it's a Calabi-Yau threefold, write dz, dx1, dx2, apply the change of coordinates, and you find again what you want to find. So this is a local Calabi-Yau thing. Then, fix one fiber of the fibration over P1, so something like this one, and think of your curve C here, and this is the singular point here. Now, there is a construction which goes back to Atiyah, I think. At least this is the oldest source I could find. So the zero section P1 can be contracted. So it can be contracted, and then you find the cone over P1 cross P1. So this is the variety of equations, something like this. But then, you see on P1, P1 cross P1, you have two different rulings. So basically, here you open the ruling in this direction, but then you can open the ruling in the other direction. And get a different threefold. So call this Y prime. So this is again isomorphic to the total space of O minus 1 direct sum 2. And there is a birational transformation here, phi, which is called the flop, which is an isomorphism outside this line and this line. And actually, if you restrict phi to this C2, you find basically this thing here, which is C2 blown up in a point, and this is the exceptional divisor. So your curve here, if you take a proper transform, will become a curve C prime here. So now what is the advantage of embedding the blow up? I mean, you can say, why don't I consider just the blow up between two surfaces? Because embedding this blow up inside the flop on three-folds allow you to use a lot of results by people like Bridgeland, Calabrese, Toda, etc., on the change. So for instance, a result by Bridgeland says that phi induces an isomorphism between the derived categories of quasi-coherent shifts on y and y prime. Okay? So this change of perspective is actually quite useful, and also quite useful was the remark by still by Diaconescu, Hu, and Soibelman, that that actually so this was a main theorem in the paper of Diaconescu, Hu, and Soibelman, is that the integral in the form in the formula, sorry, of Oblomkov and Shende is a generating function for moduli of framed stable pairs on C. So let me tell you a bit what is a frame stable pair of C. So frame stable pair on C is the datum of two things. So F is a coherent sheaf of pure dimension 1. So pure dimension means that if you, whenever you look at it over an affine open set, so you have a module of the ring of coordinates, you look at its primary decomposition, then you always have, you don't have embedded primes. You always have one-dimensional thing. And I mean, for F and, no, I mean, as I said, S is a section. So this is a section with finite dimensional co-kernel, with finite co-kernel. And also, you ask that the restriction of F to y minus E, where E is the rational curve here. So outside this, so the restriction is just the structure sheaf of the curve restricted to y minus E. Actually, you asked that I mean, this diagram, that this, let me say this a bit more precisely, otherwise it's ununderstandable. So you ask that there is an isomorphism from F restricted to y minus E to OC restricted to y minus E. Then here you have the restriction of the section, so from O y minus E. But also here you have identity, and here you have y minus E, and here you have the canonical surjection. So you ask that this diagram is commutative. So, I mean, a frame stable pair is something which outside E is just identified with a structure sheaf of C, and then something happens at the singular point and E. So frame-stable pairs, which were introduced by Pandaripande and Thomas in enumerative geometries. So frame-stable pairs have basically two numerical invariants. So the first is basically the dimension of the space of functions on the cokernel of sigma. And the second, so this is usually called N, and the second is the R. This is the generic multiplicity of F along this curve. So the sheaf F is the support of the sheaf F is C union E. And so along E can have some multiplicity. So these are basically the two invariants. So, and then there are, let's see. Okay. And for every R and N, there are moduli spaces which are called P, Y, C, R, N. So moduli spaces of framed stable pairs with those numerical invariants. So in the theorem of Diaconescu, Hua, and Soibelman is that after some normalization, basically the integral, I mean this sum S2L 1 minus V square, etc. I mean the right-hand side of the Oblomkov-Shende formula is up to a normalization the same as the sum over all R and L of S to the L minus V to the 2R times the Euler characteristic of this moduli, topological Euler characteristic of these moduli spaces. So it's hard to realize that this is actually a progress, okay? But it is, okay? because the behavior of these things under a flop are much better understood than the behavior of the Hilbert scheme. And actually, this formulation suggests a more refined version, which is actually what's leads to the proof. I mean, suppose you want to prove the conjecture. You try to prove the conjecture. I mean, the first thing you try is to understand what happens after when you blow up. So you want to, in a sense, you would like to say, okay, I have this generating function. I blow up the singular point. This generating function will change in some way. And also the HOMFLY polynomial will change in some way, which is actually something which can be understood. But the problem is that when you blow up a point here, the total transform contains now your line, but with a multiplicity. So it's better to have a framework in which you allow several components also with some nilpotent structure. And actually, this is precisely what is also suggested by Diaconescu, Hua, and Soibelman. And I I'm badly late, but I have to just at least let me sketch how this goes. So, colored version of the conjecture. So this is somewhat magic. So how do you color this situation? So coloring means that for every component Ci of C, or which is the same Li of the link, you choose a partition mu I of some integer. Okay? Choose some Young diagram. Okay. Now, you can do many things with a partition of an integer, but among the many things, there are two which are relevant to the story. So with a partition, you can construct a monomial ideal in two-variable polynomials. How do you construct it? Well, that's easy. Well, it's easy once you've seen how it works. Okay, so this is the Young diagram. So suppose that every point, the point ij corresponds to the monomial x to the I, y to the j. So this shaded region is obviously an ideal, because multiplying by x corresponding to go in this direction multiplied by y. Okay, so this is a maximal ideal, and it's actually obviously generated by monomials, so the radical is 0. Okay.
Which is the integer you consider partitions of?
Any. Yes. So the point is that consider all integers, all partitions. So you get a huge formula. Okay. So you can associate a monomial ideal, or maybe you can associate some combinatorial thing like, for instance, a sure function, sure polynomial. Sure polynomial, or maybe more or less equivalently, you can choose, you can associate an idempotent in the AK algebra of type A. But let's say sure polynomial. And what do you do? So you use these two different objects to enhance the structure you start with. And that these two things correspond to each other is, I think, very remarkable. So on the curve side, remember you have your curve inside C2, and then you have an extra dimension. So basically, you consider a thickening of this curve precisely by this ideal monomial. So for each component, at each smooth point, the local equation is just a coordinate. And then basically you put a thickened form by this monomial ideal. So you have a scheme, a non-reduced scheme structure along C minus the singular point. So this is a technical point. First you do it on the smooth point, and then you take schematic closure because you want to have a Macaulay curve, but something I don't want to discuss in 2 minutes before the end of my talk. But basically, I mean, the important thing is that you enhance your reduced curve to a non-reduced structure, which is controlled by these partitions. And then on this non-reduced structure, you still have moduli spaces of these objects depending on a partition. So you now have some big generating functions which depend not only on y and c, but also on your array of partitions. It's an array because you choose a partition for every irreducible component. What do you do on the link side? Well, on the link side, you use you use a result of 2ref, an old result of, sort of magic result of 2ref, which says that with every symmetric polynomial, say, you associate a diagram in an annulus. So a diagram means sort of knot, some generalized form of a knot, some diagram in an annulus. And then you go back to the link of your curve, which is this iterated toral knot. So if I had had more time, I would have told you that on iterated toral knot, you not only have a knot, but you also have a framing, which means that for each point, there is a choice of a non-vanishing normal vector. I mean, this is clear if your knot sits in the torus, because it's a two-dimensional thing. You have one dimension, so you can complete, and you have a, okay. So this allows you to enhance your knot to a ribbon, okay? A ribbon which is diffeomorphic to an annulus. And then you take the Schur polynomial, construct the corresponding diagram, and transplant it into this annulus, and so you have an enhanced link, and it has a colored HOMFLY polynomial. And the conjecture of Diaconescu, Hua, and Soibelman is that these generating functions up to some normalization, which is not particularly inspiring, coincide with the colored HOMFLY polynomial of L with the transposed partition V and S. And it's actually in this form which Maulik proves this conjecture, because this form is stable by blow up. I mean, when you blow up something, you get a new colored thing. And even if you start from a non-colored link, after blowing up, you have to color. So this is the form in which Maulik proves it. And of course, I don't even have time to sketch the proof. So stop here.
Drawing consequences of the first uncolored formula, right, conjecture, you made the comment that, if I got it right, that the obvious S minus S inverse symmetry on the HOMFLY side would translate into some self-duality or something like that?
Into some non-obvious consequence of self-duality, which had been noticed by...
Self-duality on...
Self-duality.
Ah, self-duality. Okay,
yes.
I'm sorry. I understood self-duality, so I couldn't make sense of it. Okay.
Self-duality, yes. But it's non-obvious. I mean, it requires some work.
Other questions? Can one hope or dream or whatever of enhancement of this formula where the Euler characteristic is replaced by Hodgson polynomials?
Yes,
or
yes,
something?
yes. If I had time. Yes, there is a further refinement which was conjectured by Oblomkov, Rasmussen, and Shende, which promotes this conjecture from Euler characteristic to some homological thing. So on the algebraic side, you have the Serre polynomial or weight polynomial of the corresponding mixed structures of the moduli spaces. On the other side, but I mean, to say that I know little about this is an euphemism. I know basically nothing, but I've been told that the HOMFLY polynomial is a sort of Euler characteristic of what is called the knot homology. Okay, and so the conjecture is that there is this can be upgraded to something, and there is a lot of work in progress, especially by Oblomkov and Kovanov, maybe, and very interesting, I think, but can't say anything particularly meaningful. But
Or if none, well, let's thank Luca.
Thank you.